But yeah, I definitely do not believe that it's just a human invention, and like that's just nonsense. There's something more, definitely something more than that.
Yeah.
All right, I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class, this time we have just to meet and study your creation. In your name I pray, Lord Jesus. Amen. All right, so let's get into it. So today we're talking about vector spaces and all that. And not just that, of course, but like the theory of dimension and all that jazz. So of course, like we're essentially in chapter 6 of my 2019 notes, which are not working like I want them to. Is my computer hung up or something? You know what? I bet this is the fault of Microsoft Teams. Teams is a cancer. No, it's not Teams. I'm just gonna kill Chrome, see if that fixes it. Oh, I don't even have my Teams open, and it's got the Teams in the background on my computer. I hate Teams so much. Oh look, well, once I close Chrome and Teams, all of a sudden I can scroll again on my PDF. Huh. Isn't that interesting? Garbage software, just garbage. Let's see here. I'll get there. So I'm skipping past the chapter on determinants because we'll deal with that later when we deal with it. And we'll come back to determinants with wedge products later in this course. That's really a wholly different view than what you saw in, your linear algebra course, of course. Oh, so much scrolling. I'm about to get sick. Okay, so let's see here. So I say up my start to the chapter, I say up to this point, the topics we've discussed loosely fit into the category of matrix theory. Jenny tells me that there's Chinese using matrices long time ago. I don't know if they were multiplying matrices, let's say, but I think they had something, well, she said they had something similar to Gaussian elimination, but it's like in a different notation and things. So honestly, if you really think about the process of like elimination for systems of equations, it would be surprising if intelligent civilizations didn't discover it on their own in some notation or another, because like just linear systems are just inevitable once you start making a mathematical analysis of systems. Like you're just going to find systems of equations. But anyway, I think these things really came into their own, roughly speaking, in the 19th century, and then the formal definition of vector space really came, around the late 19th century, maybe. I mean, it's hard to say exactly. There's snippets here and there where, like, Cauchy and other people were doing n-dimensional things, but I think, if I understand the history correctly, maybe Frobenius was maybe the first person who just kind of came and just did it. But it's really hard to find a concrete history of linear algebra because it's just so ubiquitous throughout math. It's hard to like pin down who did what first, in my experience. I'm no historian or anything, but when I've tried to look into some of these things, I've not found real clear answers to the questions that you might naturally ask. But I think the definition of vector space, man, I don't know, maybe, I think I might have it in the introduction, but I forget. But here's the typical definition of vector space. I have 10 axioms. It's very clunky. A pure mathematician wouldn't really like this. There's a more logically minimal definition you can give. So this definition is not given as a logically minimal definition. It's just given for pedagogical reasons. To summarize the definition of vector space, it's a set together with an addition, which makes the set an abelian group under addition. And then there's a scalar multiplication, which interacts with the addition in sort of the natural way. So I don't want to write down the definition of vector space because it's not, you know it. But of course, the Rn is our sort of quintessential vector space. So let me just talk about some examples. So of course, number one, we can talk about Fn over F. So to talk about a vector space, you're talking about the vector space paired with the underlying field of scalars, right? And you have to have some addition which goes from V cross V to V, right? And you have to have some scalar multiplication which goes from the field across the vector space back to the vector space, right? And our typical notation is something like x comma y maps to x plus y. That's addition, right? And then c comma x maps to c dot x. But honestly, we soon use juxtaposition for the scalar multiplication because it gets really tiring to write that dot, right? And truth be told, we also typically abuse notation and allow ourselves also to write that. Like we'll scalar multiple vectors on the right in practice in our examples, right? So I think if you were really to be more honest, the thing we use isn't quite a vector. It's more than a vector space. It's actually got scalar multiplication on the left and the right, It's what's called a bimodule. But anyway, there is a deeper thing to study here called module theory, which you can study, in abstract algebra. But that's for another course. Okay, so anyway, so Fn over F is the quintessential vector space, right? 2, of course, you can talk about matrices, right? Right, that's a vector space because addition of matrices and scalar multiplication of matrices satisfies the definition. 3, and here's a much more adventurous example. If you have S is a set and V, good grief, V a vector space over F, right? Then if we talk about F equal to like functions that go from the set to the vector space, F a function, that is a vector space. Now that's a much more complicated example than the previous two, right? I mean, S could be any set. V could be any vector space. How do you add, so I'm saying these kind of functions are quote unquote vectors in this space F. How would you add? If I had like F plus G, how would I add that?
F plus G of x equals F of x plus G of x.
F, right, so exactly, the pointwise rule of addition, and that's for all x in S, right? And how about scalar multiplication? We do C times F of x equal to? C times F of x, right. And this addition and this scalar multiplication would make sense because they're both happening where? This and this, they're both happening in the vector space, right? So, I mean, this is just a stupidly general example, right? So, and it just totally depends on the values of the function, right? Nothing interesting is really going on in the domain at all. All right, so there's that. Let's see here. Of course, you can take this example probably should have come before that one, but if, for example, if you've got polynomials, with coefficients in F, right? Now I forget how much field theory you know. Have you had abstract algebra too?
Yeah.
Okay, so also like generically speaking, anytime you have a vector space over a field, right? You can also view that vector space as a vector space over any subfield of that field. You know, like for example, just to give a kind of specific example for a change here, I can talk about complex 2 space, right? And that is, of course, over the complex numbers, a vector space, right? However, it's also a real vector space. So, alternatively, we can look at C2 over the reals, right? Oh, thank you. I was going to ask you about that. Sorry. We can talk about C2 over the reals, or more insidiously, we could talk about C2 over the prime subfield of C, right? The rational numbers. And, you know, these are the same point set, C2, the same point set, but these would be different vector spaces because a vector space is the addition paired with a scalar multiplication. All right. So that's just a quick list of examples. Of course, you can mix and match these, right? Like, you could start doing things like taking matrices of functions, and you could do many things. All right. But that's a good list of examples. And then, of course, the other sort of more specialized example would be like if we had L of V to W is the set of linear transformations from vector space V to vector space W, right? I mean, so that really is that's a sub-example in some sense, right, of 3. Because, you know, you could look at the set of all functions. Like the set of all, so if I was, maybe I should call this, I don't really have a good notation for it, but let me introduce a notation, F, S, comma, V. All right, so like L of V comma W would actually be a subspace of the function space from V to W. Now, supposing V and W are finite dimensional, right? If V and W are finite dimensional, then the function space from V to W is still infinite dimensional because it includes all kinds of exotic nonlinear functions, things you can't even think about. Whereas the linear maps from V to W are actually also, that's also a finite dimensional vector space, right? So turns out if you have linear transformations on a finite dimensional vector space, they're uniquely specified by what they do to the basis of the space, all right? So if I'm not careful, this will devolve into a linear transformation lecture. Let me not do that today because I'm a little bit tired and it would be better for me to cover easier things. Come on, computer. Computer, come back to me. So of course, to prove this is a subspace, we need that subspace theorem, right? And come on, what's going on with this thing? Every time my computer goes into its power saving mode, it like locks the thing up. All right. So the list of examples in my notes, I think, is a pretty robust set of examples there. Going on here to like theorem 6.13 and 6.114. These are just like obvious vector calculations that follow from the axioms. law of cancellation. Hopefully you did that kind of thing in your vector. You may or may not have done that in your linear algebra. It's more of an abstract algebra exercise there than anything else. Now a subspace is what? A subspace is a subset of the vector space, which is again itself a vector space with respect to the same addition and scalar multiplication. The subspace test theorem says that if you have, so theorem, right? If S is a subset of V with S not equal to the empty set and 1, x comma y in S implies x plus y is in S, right? And 2, x in S, C in field implies Cx is in the set again. I think that's it. Man, I'm rusty. That's the one formulation of the subspace test theorem, right? So if you can, so of course you could take these two and you could swap it out for, if you can show that, x, y in S, C in the field implies that Cx plus y is in S, right? Which is not empty. If you can prove that, you got it's a vector space, right? But oftentimes I forget to prove it's not empty. Like, actually, there's the thing I forget more often than not. That's really disturbing when you forget about it and somebody proves it and you realize there was something to prove there you didn't think about, is the subset condition.
Yeah.
Like, there are examples where you can deceive yourself into thinking something's a subset of something when it's not. And like that, it's almost always, though, this doesn't even, it's not almost always not even something to discuss. All right. So I forget about that at times. And usually I check for 0, because that's also, if you're in doubt, if you can show 0 is not in the thing, then it's not a subspace, right? So that's nice. So that's the subspace test theorem. Of course, there's another theorem which is important for subspaces, which is that if W is equal to the span of some set, let's say S, where S is a subset of a vector space V, all right, and this is the span over the field F, right? Then W is a subspace of V. All right. Now, I guess I should really define span, right? What does span F mean?
The set of all linear combinations.
The set of all linear combinations.
D11
Okay, but what's a linear combination?
It's any arbitrary scalar from S multiplied by any arbitrary element in S.
Mm-hmm.
Added together.
Okay. So this, yeah, I mean, that's essentially it. In words, the span is the set of all possible finite linear combinations. All possible finite linear combinations. I suppose there is a context in the Hilbert space where you might extend this notion past a finite linear combination, but that's a special context. But in regular linear algebra, span is a set of all finite linear combinations, even when S is infinite. All right, so now, of course, K is a variable here, right? But if you're working in the context of an n-dimensional vector space, you can just swap this K out and just put n here. Well, no, that's not to say. I shouldn't say that. That's not true. Rather, when S is a finite set, I should say this, when S is a finite set, that's what I mean to say, when S is a finite set, you can just sum over all the elements in S. You don't need like to index by K, but if S is finite, you can just sum, you know, you can just choose that one finite sum. You don't have to like take all I mean, there's, because, you know, if some of the coefficients are 0, you might say, well, I just need to sum 2 of them, but I've got 4. Well, okay, well, you sum 4, you just make 2 of the coefficients 0, same difference, right? But
why does it have to be finite? The sum.
that's the definition. If it wasn't finite, then theorems like the following thing would be harder. I mean, here's the theorem. A linear combination of linear combinations is a linear combination. If you allowed your linear combinations to be infinite in some kind of, like when we talk about infinite linear combinations, it begs questions of convergence. So you'd be saddled with those questions. And we don't want to think about those. We're not thinking about convergence, right? We, you know, like polynomials, we like to think about polynomials, but we don't have to worry about convergence with polynomials because even though we have infinitely many powers to choose from, we're always looking at finitely many of those things. So we don't have to think about convergences. But that's a good question. I think the answer is it's a definition. But and yes, you could think about infinite sums, and that would lead you to analysis type questions. But this is like, I don't know if you've ever thought about this, but this is really, well, the proof of the span theorem is essentially this, right?
Sorry.
The proof of the span theorem is this theorem. Because if you have, you know, if you have x and y in the span of S, right? Then, of course, you could write x is equal to, you know, a sum of ci, si, right? And y is equal to a sum of, you know, b, bi, si, right? And without loss of generality, we can assume that both of the finite sums have the same size by simply picking the one that's largest and extending the coefficients to be 0 for the other ones. So we don't have to deal with different size sums, even though logically speaking they could be. And then, so what? Cx plus y is what? You know, c times this sum, right? Which of course is again an element of so therefore, and how do I know it's not empty? Well, choose your coefficients to be 0. So the trivial linear combination gives you the 0 vector, it's not empty. And by definition, by the way, the span of the empty set is equal to the 0 vector, as to not have to make all kinds of special statements about theorems. See, if you do that, then you have, without qualification, the span of any set is a subspace. Assuming that set, of course, is a subset of a vector space. Context, right? But, yeah. And of course, you can't take, I mean, you can't just take the span of things you can't add, right? I can't just take a collection of cats and take their span, unless you've got a way to add cats. I would set them all to 0 personally, but especially the one that's been peeing on my front porch. I'm a doormat. Like, really? Oh, ugh. My son loves the cat. Anyway. Children. Let's see here. Do. That door is very schizophrenic. Like it's just, I can't decide. I'm open, I'm closed. Pay attention to me. All right. Are we good? Okay. Now, so the, if given a vector space V, so given V, and S, I probably should have said this already, a subset of V, right? Then number one, if the span of S is equal to V, then S is generating set or spanning set. Of V, right? And number two, if for all, let's say S1, S2, Sk in S, C1 S1 plus C2 S2 plus plus Ck Sk equals to 0 implies C1 equals to C2 equals to equals to Ck equals to 0. So if, and for all K and N, right? Then S is linearly independent, right? So S is linearly independent if any finite linear combination of elements from S, right, implies that the coefficients are all 0. In other words, any finite linear combination which gives you 0 is in fact the trivial combination. This is linear independence. So that's still this dance we're playing with, like taking a finite subset of the infinite is important for examples, because like, oh well, I'm erasing. It's I was gonna write what the, I want to talk about the dimension of all these examples, of course, right? But oh well. What's done is done. So dimension, like what's that, right?
Number of vectors in the basis.
Yeah. Oh yeah. I guess that. So the thing, I probably, you said a word, basis. Yeah. So words mean things, right? So let's write that down. Basis for V is a linearly independent spanning set. For V. All right. And of course, I'm assuming, as usual, V is vector space over a field. And of course, all of the spans that we're talking about are taken over this, the scalars for the spans are taken from that field, right? I think we can define the dimension of the vector space to be the cardinality of the basis. I'm not especially interested in the infinite dimensional case, so I'm not going to focus there at all. There are things you can say about it. I'm not a good person to ask about that at the moment. I have to there's nuance there that sometimes slips past me, so I try not to talk about it. Finite dimensions is my home. So if V is a finite dimensional vector space, then the dimension is the cardinality of the basis, but that's just the number of elements in the basis. So the dimension of the basis is equal to the if it's equal to the number of elements in beta, and that's less than infinity, then V is finite dimensional. All right? B is a finite dimensional vector space if there exists a basis, right? Okay, so when did we start? We start at 11:15 and we go to 12:30, is that right? Okay, cool. Just gauging. So consider this then. All right, so suppose we have beta equal to, let's say, v1, v2, vn, and we have beta bar equal to v bar 1, v bar 2, v bar, let's say, p, right? And suppose that these are both bases. These are both bases for a given finite dimensional vector space. I would like to prove for you that n has to be equal to p. Did you prove that in your class?
I think so.
Oh, okay, good.
I took a class like a year and a half ago.
Oh, okay. Oh, well. In my notes, so you already know what I'm about to say. Oh, well, I'll say it anyway. I'll say it anyway. I'll be quick though. So essentially, to prove that the n equals to p, what we can do is like, all right, so first of all, if I take any, the ith element of beta, right? Then vi is an element of the vector space V, which is the span of beta bar, right? Which means that there exists, let's say, big C I j in the field such that what? Such that vi is equal to a sum over j equals 1 to what? 1 to p of Cij v bar j. So we can do that, right? Now on the flip side, we also have that v bar, I'll use different letters here. K is in beta bar, implies that there exist, D, let's say, KL in the field, such that what? Such that V bar K is equal to the sum over L equals 1 to N of D, K, L, V, L. All right. So then what? Well, we can substitute one of these into the other, right? So like we can look at it, Vi is equal to the sum j equals 1 to p of Cij and then V bar j, right? But what is V bar j? V bar j is the sum. I'll tell you what. Let me go back to my line above and just make a slight editorial comment, just to make it easier to follow. I'm going to switch this guy to a j, because basically I'm plugging this for this, all right? And so we've got what? We've got L equals 1 to N of D, J, L, V, L. Which of course we can rewrite as Vi equals to the sum J equals 1 to, well, let me see. Let me rewrite it as sum L equals 1 to N. Yeah, L equals 1 to N. I'm going to flip the sums. L equals 1 to N of the sum J equals 1 to P. So that exchange of finite sums lemma, actually when you look at the details, matters. Cij djl, right? VL. But what's one of the fundamental, like, when you, okay, so first thing we do in linear algebra when we introduce linear independence is we come to we collect a collection of equivalent statements for linear independence, right? Like one of the equivalent statements of linear independence is that it's not linearly independent if you can write one vector as a linear combination of the others. That's kind of like, oh, okay, so that, and that of course would be manifestly a linear dependence. Fine. Another way to categorize linear independence, though, is that if you have the property that you have the equating coefficients property. So if every time we have the set and we take a linear combination from the set equal to another linear combination from the set, we can equate coefficients. That is equivalent to linear independence. It's pretty easy to see why that is equivalent to the proof that we gave, right? Because if you have two linear combinations equal, you can just put them, subtract one to the other side, regroup things, and then you'd have the difference of the coefficients times the vectors all equal to 0, which then implies that all of the differences have to be 0, which makes them 0, and this argument can go, you can go both ways. You can take that, the equating coefficients data, prove the definition I have over there, or vice versa. Okay, so with that in mind, we have this. We can use equating coefficients, see, because on the one hand I have Vi, on the other hand I have this. But equating coefficients, if you like, I can make this a sum. Sum over L equals 1 to N of what? Well, of the Kronecker delta IL, VL. Right? Kronecker deltas kill finite sums, and if you want to make Kronecker deltas spring up from nothing, just do that. But now, see, I have that this is equal to that. In other words, I have that Kronecker delta IL is equal to the sum J equals 1 to P of Cij djl, like that. Which of course is, we defined matrix multiplication last time, right? And this is exactly the P by P identity matrix is equal to the C matrix times the D matrix, right? I mean, that's it. That's what that is. Because you have the ILth component of CD is equal to the Kronecker delta, which is to say that C times D is the identity matrix. But by symmetry, we can make the same argument with the beta and the beta bar bases roles reversed. And when we do that, we get by symmetry that the n by n identity matrix is equal to DC. But then we prove the trace is equal. So the trace of IP is equal to the trace of CD, which is equal to the trace of DC, which is equal to the trace of n, IN. So that's equal to n, and that's equal to P. And there you go. Dimension, if you have a linearly independent spanning set, the dimension has to be equal. And I was telling you last time there's other ways to prove this, but I'm fond of this way. It's very calculational. Yeah. Actually, a very similar kind of argument is used in my thesis concerning like superdimension stuff. But anyway. All right. Great. So moving along here, we'll look at examples soon, okay? But just a little bit more theory here. Get under our belt. If you have a basis, right? If you have a basis. So definition, if beta equal to, let's say, V1, V2, Vn is basis for V over F, right? Then, this is mostly my notation. I don't know if anybody else uses this notation. It's just my notation. Then phi beta is a mapping from V to Fn defined as follows. Phi beta of Vi is equal to Ei for all I equals to 1, 2, dot to the n extended linearly. I'm using a theorem, which I probably should prove before I make that definition. Sorry, I put the cart before the horse. But the theorem I should prove is that, I guess I need to define linear transformation for one thing, right? What's a linear transformation? We'll get back to this. Sorry, I kind of got out of order here. So definition, if you have given VW vector spaces, right? And L a mapping from V to W a function, right? Then the L is linear transformation if L of x plus y is equal to L of x plus L of y, and L of Cx is equal to CL of x for all x and y in the vector space and C in the field, right? In other words, a linear transformation is a transformation from one vector space to another which preserves the structure of the vector space, which is why if you read a more abstract algebraic book about vector spaces, they'll actually call these homomorphisms, because that's what they are. All right. There's no expectation, of course, that it's one-to-one and onto, right? So that's why it's just a homomorphism. Now, if in addition the linear transformation is a bijection, then we say that it's an isomorphism, right? So if L is one-to-one and onto, then L is isomorphism. So many things to say here.
And if B equals W, then we call that an endomorphism?
Oh yeah, V equals to W, then it's called an endomorphism.
And it has to be an isomorphism to be an endomorphism.
Well, no, I don't think so. I think endomorphism just means homomorphism from the vector space to itself. I want to say isomorphism from the vector space to itself would be an automorphism. But I should check on that. As, like, you know, my life is not full of people asking me these questions. I'm a little rusty, but I think that's right. All right. Okay, so, great. There's all kinds of theorems you can prove. Like, here's a theorem that you can prove that's interesting to prove. Theorem, if the kernel of L, which by the way is equal to x in V such that L of x equals to 0, right? If this is equal to 0, then L is injective. And, that's one, you can prove that. And two, if L is injective and S is linearly independent, then L of S, which of course would mean what? L of S would mean L of SI, such that SI is an element of S, right? Yeah. Is what? It's linearly independent, all right? So like injective linear mappings maintain linear independence. That's interesting geometrically, right? That means that if you feed a line, a set of points which is aligned to a linearly independent, an injective linear transformation, the range, the image of it is aligned. If you map a plane into an injective linear transformation, the image is a plane. A volume maps to a volume, right? So this also means sometimes if someone hits you up here with a hypothetical, example. Well, maybe this is just a remark, right? If the dimension of W is less than the dimension of V, then L of V I didn't want to say L of V. I want to say L from L from V to W, all right, is not injective. Why? Because you could take the basis for V. If L was injective, it would give you a linearly independent set. That would be the image. But then you'd have a set of vectors that was linearly independent inside W, who had more vectors than the basis for W, which is impossible. If you have a spanning set which is linearly independent and you adjoin a vector to it, it's necessarily a linearly dependent set. That's that plus minus theorem I was talking about last time. Yeah. So this is actually this is the junk that makes great GRE kind of questions, right? It sounds really, I don't know, but if you just think about it, you can answer a vast number. Of course it could be dressed up in more, fancy clothing. You can have, L's from R6 to R3, and they could bury you with a bunch of formulas and then say, is L injective? But all you need to do is look at it and go, 6, 3. No, it can't be injective. You have to do something with that 6 dimensions. Like the linear transformation, the domain of a linear transformation is the totality of the vector space. Right? Now, could you restrict the linear transformation to make it injective? Sure, you could do that. That essentially amounts to, you could, if you took the quotient space by the kernel, that would give you something that basically squashes that departure, the multiple valuedness down so that it becomes injective. We'll talk more about that some other day. I don't want to get into that today. All right, so getting back to my definition, I extended linearly, right? So does that make sense now? At least, So extended linear means that phi beta is a linear transformation. And so like, all I'm really saying is that if I have x equals to a sum, right, of ci vi, I equals 1 to n, of course that can be done, right, because it's a basis, then phi beta of x equals to what? Phi beta of the sum I equals 1 to n of ci vi, right? Now, when I talk about extending a linear transform, extending a map linearly, the claim I'm making, I'm sorry, I still haven't gotten to my theorem. My bad. I mean, I'm going to exhibit the proof of the theorem in a specific case here. And I will state the theorem again here once I get this out of my system. I probably didn't need to say all this, but I have no regrets. Well, that's not true. But with regard to this lecture, I'm okay. Mostly. Actually, did I turn the sound on? La la. Okay, good. Yeah, we got music. We got audio. All right. Okay, so if phi beta is a linear transformation, which is what we mean by extended linear, is like assuming linearity. That means you can pass the sum out, right? Ci and then phi beta vi, right? In other words, it's the sum I equals 1 to n of ci ei, which of course we could write as c1, c2, cn. But really, the definition of the definition of the coordinate map, right? Phi beta is the beta coordinate map. At the heart of it, what you're saying is you're defining the map by saying I'm changing the abstract basis v to the concrete standard basis, like ei, all right, 1, 0, 0, 0, with with a 1 in the ith position. The theorem that I'm butchering at the moment is that if v is equal to the span beta where beta equals to v1, vn is basis for v, and we're given w1, w2, wn elements of w, another vector space, all right, then there exists a unique linear transformation L from v to w such that L of vi is equal to wi for all I. This is the linear extension theorem, and it's super useful because it means you don't have to give a formula for the arbitrary vector. If you give a formula for an arbitrary basis element, that suffices to define the linear transformation altogether. And the proof of this theorem is essentially what I have in the definition right there, right? It's like, see, what do we mean define uniquely? Well, if I have L of x, right, I can say, well, that's really L of the sum, I equals 1 to n of like ci vi, right? Just assuming the same notation as up there. And then that's going to be the sum. And so this right here now is a definition. Okay, I'm saying you can define L by this rule. Sum I equals 1 to n of Ci Wi. Definition. And why was that unique? Like, let's think about why would that be unique? This is why it needs to be a basis. If beta is a basis, the coefficients that define x as a linear combination of the v's are uniquely given. If it was not a basis, you could choose different linear combinations here, which would then give you different formulas here. So it wouldn't be a unique linear transformation in that regard. But it is, so this formula is uniquely prescribed. That's where the uniqueness comes from in my view. And then, okay, what about, and then you think about this, okay, so what if we just feed it just Ci with all the, so like think about when all the coefficients are 0 except for 1, which is 1, then this formula just drops back to like L of V1 maps to W1, right? The formula reduces to the assumption that Vi maps to Wi in that case. So, and then what remains is to prove that this actually defines a linear map. But that's just a routine calculation, because if you have x plus y here, you get coordinates of x plus coordinates of y for the coordinates of x plus y. That goes here, and then it just, I mean, linearity is a simple exercise. So this is the linear extension theorem. If we define a linear transformation on a basis, that's enough. You got to understand, we don't have this theorem in general abstract mathematics. If I give you a function from the reals to the reals, for example, and I tell you f of 2 equals to 3. Now tell me f of x for all other x. You'd laugh me out of, you'd be like, no. But if I told you, you have a linear function from reals to the reals, f of 2 equals to 3, well, that uniquely prescribes the function. See, because then we're talking about f of x equals to mx, right? And if I have f of 2 equals to 2 times m equals to 3, that tells me m is equal to 3/2, and so I'm done. That's the unique linear function that sends 2 to 3. And so, yeah, linear algebra is extremely, the structure here is so, in some sense, restrictive, but in my feeling, freeing, because it allows, even though vector spaces have infinitely many vectors, we're able to capitalize on this finiteness of the basis to make, you know, concrete arguments which allow counting, which allow induction, so many of these things. The same thing happens with my thesis, except it's with super dimensions, so it's over spans of super numbers rather than reals. But anyway, so that's the coordinate map. Now the coordinate map is in fact an isomorphism. How do I know that the coordinate map is an isomorphism? Oh, that clock is really wrong. I thought there's a lot going on in the hallway for it being 20 minutes before the end of class. Oh, wait a minute. 20 minutes before the end of class. Wait, no. It's 12:30 until this period lets out. Yeah. It's actually 12:21. I mean, that says 12:13 or something. I need to get some tall person to fix that, you know? Okay, so to prove that the coordinate map is an isomorphism, how about this? Well, let's see here.
So we call this map the coordinate map.
Yeah, phi beta is the beta coordinate map.